In part 3 of the AP Physics 2013 course, in test 8, we're looking at problem number 20. The only force acting on a 2.3 kilogram body as it moves along the x-axis varies as shown below. The velocity of the body at x equals 0 is 14 meters per second. I did a very similar problem except with a different initial velocity in class. So what we're looking here is finding the work done because we want to find the speed of the ball, and we know that the net work done on an object is the change in the kinetic energy, which is 1/2 the mass times the final speed squared, which is what we're looking for, minus 1/2 the mass times the initial speed squared. Well, I have the initial speed right there. VI is 14.0 meters per second, and I know the mass is 2.3 kilograms. So I know this, I know this, I know this. I'm looking for that. If I could find the net work, I could rearrange it and solve for VF. So let's go ahead and do that. 1/2 mVF squared is equal to W net plus 1/2 mVI squared. Let's divide both sides by m and multiply by 2. VF squared is 2 W net over m plus VI squared. So the final speed is the square root of 2 times the net work over the mass plus the initial speed squared. So I need to find the net work. Now I can do that because they told me what the net force is, and W net is the area under the force position graph. So I've got a positive area here, I have a negative area there, and then I have this rectangle. And if you look at it carefully, you'll see that in fact the positive rectangle and the negative rectangle actually canceled. I'll go ahead and calculate them as if I don't notice that, but I do really, and so I would have knocked this with this, and all I really need to do is multiply 3 times minus 4 to find this area. But if you don't see that, it's okay, it won't hurt you. You just need to calculate and add those rectangles up. So 1/2 times 1 meter times 4 newtons, that'll get you this little triangle right there, plus 1/2 1 meter minus 4 newtons, that'll get you the area of there. Notice that the height is a negative, it's a negative area, plus 3 meters times minus 4 newtons. That gets you this rectangle. Put all that together and you find that there was a minus 12 joules of work. Now that I have that, I can put that in this equation here. So the final speed is approximately the square root of 2 times minus 12 joules divided by the mass of the object was 2.3 kilograms plus 14 meters per second squared. Put all that together. This is going to do, there's negative work, it's going to slow down, so this will be less than 14, but 2 over 2 is about 1 minus 12. 14 squared is 196, so this is going to dominate this, so it's going to be just a little bit less than 14, and I came out with 13.6 meters per second. Alright, moving on. That finishes all the rest of the regular problems. We're now into the bonus. The first bonus was just a demonstration that you can find a dot product, which is important for calculating work. Remember that if they're in Cartesian form, A dot B is the x component of A times the x component of B plus the y component of A times the y component of B. I did a couple of these during class. So The x component, that's 3. And I multiply by the x component of b, which is minus 7. So 3 times minus 7. And then I have a minus 5. And I multiply that by a minus 2. So minus 21 plus 10 gives me minus 11. Number 2. Number 2 is similar to what I did in the video. In fact, I did this calculation, just a different force. It asks you to calculate the work across a path. Along each path, you have to figure out how to describe the path, and you have to figure out what the displacement is in the path. So I'm going to break this into 2 parts, this part and that part. In the first part, whoops, ran into my microphone there. My force and my displacement are as this. Delta R is going 2 units up in the j-hat direction. So F dot delta R is going to be the x component times the x component. So that would be y squared, the x component of this, times the x component of that, which is 0. Plus the y component of the force, which is 6, times the y component of r, which is 2, and of course all of that is in joules. And that's the work. So the work is equal to 12 joules on the first part. I'll call that path 1. Then now we know we gained 12 joules of energy there. We got to do some work going across path B. In this path, we know something. Y is equal to 2 along that path. So the force is equal to 2 squared I hat plus 6 j hat makes it 4 I hat plus 6 j hat. The delta R, the displacement, is 1 unit in the I hat direction. So work 2 is the force dotted into the displacement, which is the x component here, which is 4, times the x component of delta R, which is 1, plus the y component of the force, 6, times the y component of delta R, which is 0. So that's 4 joules. The 4 joules of work was done in the second part of the path. The total is W1 plus W2, 12 joules plus 4 joules is 16 joules. That's the total amount of work that was done in this path. And now the final problem in this section, which is also off of something that I did in the videos. This is a box is sliding across a rough level floor. Blocks like that. The block has a normal force up. It's a level floor. It has a weight down. It has a friction force like this. It's being displaced in this direction. It's initially with a speed of 3.5 meters per second. It traveled a distance of 1.6 meters. It came to rest. What is the coefficient of sliding friction for the block floor system? The work is equal to the force, in this case the friction, this is the non-conservative, the work by friction, times the displacement, times the cosine of the angle between this vector and that vector, which is 180 degrees. Cosine of 180 is minus 1, so this is minus the friction force times delta R. Delta R, I know from up there, is 1.6 meters. The friction force from previous chapters is the coefficient of static or kinetic friction times the normal force. Well, looking at this free body diagram, I have the following. The sum of the forces in y is MAY, but there's no acceleration in y. The normal minus the weight is 0. Therefore, the normal is equal to the weight, which is mg. So the friction force is mu mg. Therefore, the work by non-conservative forces is minus mu mg delta r. So we're getting close to actually having everything we need. We have that mu is minus the work by non-conservative forces over mg delta r. I just need to find the work by non-conservative forces. Now when I look at this block back here, the work by gravity is 0 because it's perpendicular displacement. The work by the normal is 0, it's perpendicular displacement. The only force doing work is friction, so the work by friction is the net external force. I'm going to put that in. That's 0, that's 0, that's W net is equal to delta K, which is K final minus K initial. But it stops at the end. It's at rest. So Wn sub c is minus 1/2 the mass times the initial speed squared. So now we can plug that into this problem. Taking this and plugging it up into here, mu is equal to minus mvi squared over 2 mg, and another minus sign out front, times delta r. The mass cancels, these minus signs cancel. So it's vi squared over 2g delta r. Mu is approximately the speed, 3.5 meters per second squared, over 2 times 9.8 meters per second squared times 1.6 meters. Put all that in, 0.391. That's the coefficient of kinetic friction. And that's the end of test 8.